Okay, in this presentation we are going to look at simulation and analysis of the exponential distribution using the inverse transform method. So we've got a little bit of an exercise here. This involves simulating samples from an exponential distribution, analyzing their means, and examining the application of the Central Limit Theorem. Okay. So we have a couple of exercises here. So exercise A, simulate 10,000 samples from an exponential distribution with rate parameter 3, each of size n equals 10, using the inverse transform method. Okay. You should save the generated values in R for later use. So we're going to use them successively over the exercises. You must use the command setSeed 3202 to initialize the random number generated before you start the simulation. Okay. Then we're going to plot a histogram of the means generated in exercise A using the appropriate option in R for plotting the histogram on the probability density scale. Okay, that's an important little item there. Plot the distribution, the probability density function, I should say, of the sampling distribution of the sample mean under the Central Limit Theorem, corresponding to the samples generated in exercise A. The graph of the PDF should be superimposed on the histogram produced in exercise B. Okay, so essentially what we're going to do is see does the sample distribution match up with the idea of the normal distribution. It should. Comment on the sampling distribution of the sample mean and the application of the Central Limit Theorem in this case based on your answers to exercise B and C. Okay. Well, first off, let's just talk about the inverse transform method, just to remind ourselves about that. So here is what we want to do. We want to generate a sample of exponential random variables, okay? And to do this, we use what is essentially the cumulative distribution function, or something that is based on the cumulative distribution function of the exponential random variable. Okay, so here's a brief explanation of the components. X is an exponential random variable that you want to simulate. Lambda is the rate parameter of the exponential distribution, and we're told to use lambda equals 3. And U is a uniform random variable on the interval 0 to 1. By generating a uniform random variable U and applying the formula, you should be able to obtain a random variable x that follows a exponential distribution with rate parameter lambda. Just a quick remark there. It says 1 minus u, but in practice you can just substitute that with u because u and 1 minus u have the same distribution essentially. So we'll keep going anyway. So we'll just stick with what the formula as given, but we'll just not take that shortcut even though it's perfectly valid. So exercise A, simulate 10,000 samples from the exponential distribution with rate parameter 3. N equals 10 and rate parameter equals 3, lambda equals 3, okay? So we're going to set the seed, 3202, and we're going to specify that the numbers in each sample is 10. So when we're going to generate a random number, it's going to generate 10 uniform random numbers each time. Lambda is equal to 3. That's going to be a constant. So what we're going to do is set them up in a matrix. Okay, so we're going to call this matrix M1 and initialize it with values of 0. And there's going to be 10,000 rows, which is 10 to the power of 4. And the number of columns is going to be n. In this case, it's 10. Okay, so we're going to create a for loop here. So for I in 1 to 10,000 or 10 to the power of 4, we're going to complete the following steps. So there's 3 steps here. U equals R unif, or runif as I call it, but it's actually R unif. N is the sample size, okay, and that's 10. So generate 10 random numbers between 0 and 1, okay. M is the generate the samples in the row. So essentially what we're going to do here is transform those values u into exponential random numbers using the inverse transform method. So it's minus log of 1 minus u divided by lambda. So it's a straightforward enough calculation really. And here's the last step. We are going to place those 10 numbers into each row successively of our matrix. So M1, I, that's the row index, is M. So it's just going to fill up row I with that sample, okay? And just runs through that for 10,000 steps. So this is what it should look like. Okay, so that's the first 6 rows and the last 6 rows. And we have the 10 columns there. Okay, so that's just actually a general idea of what we are creating. And so each step of the iteration of the for loop, we just fill it up row by row. Okay, so that's that one done. Exercise B. Plot a histogram of the means of the sample. Okay, so what we're going to do here is first off get the means of each row. Okay, we've saved that up as M1, that matrix as M1. So what we're going to do is get the compute the mean of each row. So how do we do that? Well, we apply M1. 1 means row-wise and mean. So essentially, this just generates the mean of each row. So what we end up with here with X bar A is 10,000 values, which are the sample means from each row. The row means are the sample means, each of the 10,000 sample means. We're going to create a little histogram of that. Frequency equals false. Okay. And importantly, just to annotate your graphs. I had to pause for a second there because my parents were trying to contact me. You might have heard little pings. Anyway, annotating the graphs. So we put in there mean equals sample distribution of X bar, which is the sample means. And let's have a look at that. There we go. You can put in a little bit more detail into it if you want, but really that fulfills all the conditions that we require. Okay. So, key characteristics of the exponential distribution. So the mean of the exponential distribution is basically, cut a long story short, it is the inverse of lambda. So the exponential mean is 1 over lambda, okay, where lambda is the rate parameter. The standard deviation sigma, this is the spread of the distribution, and it is the same as the mean. So sigma equals 1 over lambda. Okay. Now this is important here. The standard error, this measures the accuracy of the sample mean as an estimate of the population mean. Okay. But just to sort of cut to the chase, for this case, the standard error is sigma divided by the square root of n, which is 1 divided by lambda times the square root of n. Or in other words, 1 divided by lambda, the square root of lambda squared times n. Okay, now that's going to be important later on because that is the mean there and the standard error are essentially the parameters for the sampling distribution, which is the bell curve that we're going to see shortly. Okay. So, plot the probability density function of the sampling distribution under the central limit theorem. Okay, so this is what we're going to do here. We have the histogram here that we have created previously, but what we're going to do is put a curve across that plot. Okay, so how do we do that? Well, there's two things we have to set up. First off, we're going to set up a little grid of x values. This is just to sort of that the curve will be based on these values, okay? They're the x values of the plot, okay? So, of the curve that we're going to create. The y values is using the d-norm function, and the inputs are the x grid values, 0 to 1 in steps of 1,000. So this is d-norm, this is the normal distribution. And what are the parameters of the normal distribution? Mean, which is 1/3, 1 over lambda, and the square root of 1 over 90. That is the square root of 1 over lambda squared times n. 1 over 3 squared times 10. That is where that comes from, okay? And color equals red, okay? So that's how the distribution of the sample means match up to what we would expect under the central limit theorem for the distribution of the sample means. That's good enough, I think. So based on the histogram and the superimposed probability density function, comment on the sampling distribution of the sample mean and the application of the central limit theorem in this case. So it is the sampling distribution of the sample mean is relatively asymmetrical compared to the normal distribution. That's to say that it just has a slight skew, basically. Nothing major, but it is evident. The central limit theorem does not work well here as the sample size is very small. So maybe you can try it out for larger sample sizes and maybe it will match up a little bit better. Okay, you can have a go, n equals 30. Okay, so Yeah, to wrap up, this exercise illustrates the process of simulating data from an exponential distribution, analysing sample means, and understanding the limitations of the central limit theorem with small sample sizes.